Today, we finish up our three-part series on the Gram-Schmidt orthogonalization process and orthogonal complements. Let's begin with a review of the process. Say that V is a vector space over either the real numbers or the complex numbers, and let's fix an inner product angle bracket. Let's say that W is a subspace that's spanned by a linearly independent set S in terms of vectors W1 through W sub k. We'll define a new set S prime in terms of V sub 1 through V sub k recursively as you see on your screen. Then S prime is an orthogonal set of non-zero vectors that also spans W. Recall that orthogonal set means given any two distinct vectors Vi and Vj, their inner product Vi with Vj is equal to 0. Now say that W is the span of some orthogonal set S prime. Then S prime is a linearly independent set, and every vector y in this subspace W can be expressed uniquely as you see here on your screen. The point is that even though the V sub i's form a basis for our set W, the more important statement is that we can actually find the scalars which give us the linear combination. In this case, those scalars are just the ratio of the inner product of y with Vi divided by the inner product of Vi with itself. Finally, say that our subspace W is the span of S prime prime, which is an orthonormal set. This means that it is an orthogonal set such that the length of each vector Ui is equal to 1. Then S prime prime is a basis for W, and moreover, every vector y in our subspace W can be uniquely expressed in the form that you see here on your screen. This is very similar to the previous statement. The only difference is that the length of the vectors, the norm of the ui, is equal to 1. So there isn't really a denominator to worry about in the linear combination. We'll use all of this to give a definition. Again, say that V is a vector space over either the real numbers or the complex numbers, and we'll fix an inner product. The act of turning a linearly independent set S into an orthogonal set S prime is called the Gram-Schmidt orthogonalization process. We'll explain more here. Say that we do wish to write an orthonormal basis beta. The construction goes as follows. First, let's choose any basis gamma in terms of vectors W sub I. Second, we'll construct an orthogonal basis in terms of vectors V sub I, as you see here on your screen. The point is that V sub 1 equals W1, and V sub I equals, recursively, Wi minus a certain linear combination of the previous V sub j's. And third, we'll construct an orthonormal basis, U sub I, in terms of the vectors V sub I, by simply taking the vectors V sub I and dividing them by the norm. Here's a quick example. Let's say that V is the span of the following three vectors in four-dimensional space. We'll choose the angle bracket, our inner product, to be the standard inner product. We'll construct an orthonormal basis beta as follows. First, we construct an orthogonal basis just by using the recursive definition. Recall that V sub 1 always equals W sub 1. V sub 2 we can write as W2 minus a scalar times V1, and in this case the scalar is the inner product of W2 with V1 divided by the inner product of V1 with itself. And finally, we'll define V sub 3 in a similar way as W sub 3 minus a certain linear combination of V sub 1 and V sub 2. The desired orthonormal basis can be found by taking these vectors v1, 2, and 3 and just dividing by their norms. So for example, u sub 1 here is v1 divided by the norm of v1, and similarly for u2 and for u3. For today's lesson, we'd like to go over a motivating example to get some intuition behind the definitions we'd like to make. Let's say that R2 is the real plane, and we'll consider the standard inner product as before. Recall that we have an orthonormal basis in terms of the vectors u1 and u2. Here, a and b are real numbers, not both 0. The theorem we begin today's review with says that any vector, lowercase v, can be expressed as uniquely as a linear combination of these two vectors, u1 and u2. Explicitly, let's denote the one on the left, which we'll call v perpendicular, as this vector in terms of u sub 1, and the second one on the right, which we'll call v parallel, in terms of linear combination of u sub 2. We want to give a geometric interpretation of all of this. So let's let W be that line, which is the span of the vector u sub 2. We can think of this line as just a set of points such that ax plus by equals 0. We'll also denote, which we'll call W perp, or W perpendicular, as the span of u sub 1. This is the line that is perpendicular to the first line W. We can think of this as the set of points such that bx minus ay equals 0. So again, W here is a line, and W perp is just the line that's 90 degrees to the first line. We're going to use all of this to define a linear transformation from the vector space V to itself as that map that takes a vector lowercase v and sends it to lowercase v parallel. We're going to call this the orthogonal projection on to W. Here's a picture. You'll see the line at the bottom is literally our line W. This will be the span of u sub 2. So let's say that we have a point V, which will be our blue arrow. What we'd like to do is take this point V and consider how it looks along the black line, which is our line W. Remember, this is ax plus by equals 0. Here we'll denote this as V parallel in terms of the periwinkle color. Again, you'll see that V parallel is here along the black line, which is the same thing as our line ax plus by equals 0. We then have the red arrow, which is the one left over. This is what we're calling V perpendicular. Again, V perpendicular here should be at 90 degrees to the line W, so V perpendicular must lie on what we're calling the line W perp. You can see here that really we have a right triangle. The point is that the blue line is our original vector V, and we're trying to take our blue line and deconstruct it into two different parts. First, we have the periwinkle, V parallel, and then we have the red, V perp. Really, this projection map says that we can take any blue line and break it into two. But actually what the projection map does is it just looks at the periwinkle that's along the black line at the bottom. So we do see that our projection map should project onto every point on the black line. So that is that the image of our projection map is just the entire black line, our space W. The null space, that is everything that projects to 0, should be all of the points along the red line. We'll see here that all of the points along the red line are what we're calling W perpendicular. So now we can see that we've actually taken the space R2 and we've deconstructed it so that we have two canonical directions. One is along the line W. This will be the image of our projection map. And the second is along the red line, W perp. This will be the null space of our map. Geometrically, you can see here that if we look at the point V, the closest that point can get to the black line at the bottom must be the length of the vector W perp. In other words, it's this well-known expression that you see here on the screen. We're going to use this now to define the concept of an orthogonal complement. Say that V is a vector space over either the real numbers or the complex numbers, and let's fix an inner product. Given a subset S, we define its orthogonal complement as the set of vectors x such that the inner product of x with y is the zero scalar for all y in the set S. The symbol is read as S perp, which really means S perpendicular. We have a few statements we'd like to make. Let's say that W is any finite dimensional subspace of our vector space V. First, W perp is also a subspace of V. Second, W and W perp only intersect at one point, namely the origin. Third, for any vector y, there exists a unique vector u in our subspace W and a vector z in our subspace W perp such that y equals u plus z. Moreover, this vector u is the unique vector in our subspace W that is closest to y. We can think of all of this as we did on the previous slide. The idea now is that we have, instead of a line, we have a general subspace W. And instead of the line that's at 90 degrees, we have another subspace W perp. Instead of writing our vector v as v perp thus v parallel, we can take any vector y and write this uniquely as u plus z. Finally, if v is finite dimensional, we say that the dimension of w plus the dimension of w perp is equal to the dimension of v. We're going to talk about the proof now. We'll see in the proof that there exists in general a linear transformation, which is this projection map along W, that sends a vector y to our vector u. We're going to show that the image of this map, that is the range, is the subspace W, and the nullity of this map, that is the null space, will be equal to W perp. Observe more generally that for any y in our vector space V, and for any x in the subspace W, then the norm of y minus x is greater than or equal to the norm of y minus the projection onto W. Let's show the first of these four statements. Theorem 1.3 says, in order to show that W perp is a subspace, we actually have to show two statements. First, we have to show that W perp contains the zero vector. Well, the inner product of the zero vector with any vector y in W must be the zero scalar. So by the definition of W perp, the zero vector is an element of W perp. Second, we have to show that W perp is closed under linear combinations. Let's take any collection of vectors x sub I in W perp, and now let's take any linear combination of those, which we'll call here x. For any vector y in our subspace W, we can consider now the inner product of x with y. This will be a sum of inner products of xi with y. But now each xi is in W perp and y is in W, so by definition, the inner product of xi with y is 0. So if we sum over 0, we find 0. This is the same thing as saying that x must be in W perp because, again, the inner product is 0 for all y in W. Now we show the second statement, that is that W and W perp only intersect at one point, namely the origin. First, we'll show that the singleton set consisting of the zero vector is contained in the intersection. Well, we've just shown that W perp is a vector space, and the zero vector is always an element of a vector space. So the zero vector must be both in W and W perp, and hence in the intersection. Conversely, we're going to show that the intersection must be contained in the singleton set consisting of the zero vector. To this end, let's say that a vector v is in the intersection. Well, first we can denote x as v. This is in W perp. And let's denote y as v. This is in W. But now the square of the norm of v is just the inner product of x with y. Again, we've just chosen x to be v and y to be v, which is 0. This is because the definition of W perp is that for any vector x in W perp, the inner product of x with y is 0 for any y in W. But now the norm of v must be 0 as a scalar, so v itself must be 0 as a vector. So we conclude now that any vector in the intersection must be the 0 vector. Now we'll show the third statement. Let's pick any y in V. We have to show that there exists a unique expression y equals u plus z, where u is in the vector space W and Z is in the orthogonal complement W perp. First, we're going to show that there exists at least one such expression. Since W is a finite dimensional vector space, we can use the Gram-Schmidt process to show that it has an orthonormal basis, which we'll denote as S prime prime. Let's denote U as a linear combination here of the U sub i's, where the scalar we write in terms of Y. So U here equals the sum of the inner product of Y with UI times the vector UI in our orthonormal basis. We'll denote Z as Y minus this vector U. From the way we've set everything up, Y must be U plus Z, and the vector U is a linear combination of the basis elements from S prime prime, so U must be in the span, that is, U must be in W. So in order to show that there exists at least one such expression as before, we must show that Z is in the orthogonal complement. But we can do this as follows. Let's pick any lowercase w in our vector space W. Then we know that our lowercase w must be a linear combination of the elements from S prime prime. So now let's consider the inner product of Z with this vector lowercase w. We're going to substitute in that Z is equal to Y minus U, and that U is a linear combination of the U sub i's. Putting all of this together and realizing the fact that the inner product of U sub I with U sub j must be either 0 or 1, we then find that things cancel out, and the inner product of Z and W must be 0 for any lowercase w in our vector space W. So by definition, we see that Z must be in the orthogonal complement. This does show that we have at least one such expression, Y equals U plus Z, where U is in capital W and Z is in its orthogonal complement. Now we have to show that there exists at most one such expression. So, by way of contradiction, let's say that maybe Y equals U plus Z, which also equals U prime plus Z prime. Let's denote lowercase v as U minus U prime, which, by looking at some algebra, is the same thing as Z prime minus Z. Now, U and U prime are in our vector space W by assumption, so the difference U minus U prime must also be in W. Similarly, Z and Z prime are in the orthogonal complement, and the orthogonal complement is a vector space, so its difference, Z prime minus Z, must also be in the orthogonal complement. Now this means that the vector v that we've just defined must be in both W and its orthogonal complement. So we see that v must be in the intersection, showing that our vector v must be the 0 vector. This means that u equals u prime and z equals z prime, so we indeed have at most one such expression. Now, let's say that x is any vector in our vector space W. We'd like to consider the norm of y minus x. Simply put, we're going to use the fact that y minus x equals u minus x plus y minus u. Now, u minus x must be in capital W because both u and x are in our subspace W. Y minus u must be in the orthogonal complement because based on our notation, y minus u is equal to z, and z is by definition in our orthogonal complement. But since u minus x and y minus u are in our different sets w and w perp respectively, the inner product of these two vectors must be 0. So the idea now is that the square of the norm of y minus x is equal to the square of the norm of u minus x plus the square of the norm of y minus u. Now, simply using the fact that the square of the norm of u minus x must be greater than or equal to 0, we'll then find the desired inequality. That is that the norm of y minus x is greater than or equal to the norm of y minus u. Let's show the final statement. Assuming that V is finite dimensional, The Gram-Schmidt process says that we can find an orthonormal basis S double prime, which means that we have our projection map as before. As we stated earlier, the image of this projection map must be the subspace W, and the the null space of such a projection map must be the orthogonal complement W perp. The dimension theorem now says that the dimension of W plus the dimension of W perp must just be the rank plus nullity of this projection map. But the dimension theorem asserts that the rank plus nullity is the dimension of V, which completes the proof of the theorem. Thanks very much for watching.